Hello everyone, today my topic is graph neural network. My name is Wang, and I come from Department of Biomedical Engineering. I will introduce my topic from these two sections, which is background and methods. So first, what is the graph? There are many examples in our daily life. For example, the social network. It can be modeled as a graph because human can be connected according to some kinds of relationship. For example, I have some friends, so I will be connected with them. The next example is that there is a website called Connected Paper. So that will connect the paper by their citation. So let's say in my paper I cite two papers. So my paper will be connected with those two papers. And the last one is the most famous one. It is called Google PageRank, because Google want to do the recommendation for the customer about the Google pages. So they just model all of the pages as a graph and do the rank of them. And according to this benefit, they will do the recommendation for the customer. So why we need the graph neural network? There are so many data that cannot be modeled as image or text, because as we know, image is a kind of grid structured data and text is a kind of sequence structured data. But as we discussed above, these three data cannot be modeled easily by image and text because they are non-grid or non-sequence. But as we said, they can be easily modeled as a graph, so we can do some learning process based on the graph structure. So here, the prior works proposed the graph neural network to learn a graph information. Okay, so let's introduce some method about the graph neural network. First, what is the spatial-based GNN? In spatial-based graph neural network, it contains two parts. One is the aggregation, and the second one is the readout. So let's say here we have a graph, and it consists of different kinds of node feature. H1, H2, H3, H4, H5 means the node feature. And after the aggregation, I will update each node feature by its neighbor. So let's say I will update the feature for H3 by H1 and H2 and H4's information. So after that, we do the readout process to transform the whole graph information into a single feature. So that will make us enable to do some kind of processing based on the whole graph, such as the classification, graph detection, or so on. But here's we have a question, but how to do the aggregation and readout? So different kinds of methods have different kinds of aggregation and readout method. First, let's see the neural network for graph. In this kind of method, we actually do first we do the graph embedding, because we need to transfer the node feature from low layer to high level, from low level to high level information feature. So for example, I will add one weight to the H3 from 0 layer to the first layer. So that will finish the graph embedding procedure. And after that, we do the aggregation. In this method, the aggregation is kind of like we sum up all the neighbors' features. So we can see that in here, we add H1, H2, H4 together and add one weight to it. After that, we kind of like add one more information about the node itself. So as you can see here, H30 means the initial node feature of itself. So this method actually used the information of both neighbors and the node itself. So what about the readout of this method? It is very simple. We actually calculate the mean value of each layer graph and then do some weighted sum of these three mean values. And then after that we will get a single feature for the whole graph. But as we said, we utilize the neighbors and the node itself information, but we kind of forget about the degree information. Because let's say for H3, the degree equals 1 will give us 3 nodes, H1, H2, H4. But if we set the degree as 2, it will give us H5. The previous method only utilized H1, H2, H4, but yet forget about the H5, because H5 is kind of connected to H3. But the situation is when the degree is 2. So here we have the second method called diffusion convolution neural network, DCNN. In this method, the aggregation part is actually contains of different kinds of degree information. For example, in the first layer aggregation, we sum up all the node features together and calculate a mean value. And the second, these node feature is according to the node degree equals to 1. And at the layer 2, we do the aggregation based on the node that whose degree is equals to 2. So in this way, we use the information of neighbors in different depths. And for this method, the readout is more simple. They actually concatenate all of the layers of each graph and times a weight matrix. Then we get the feature for the whole graph. So we discuss about the neighbors and the degree information respectively. So how about if we can combine them together, will it be better to develop a more better algorithm? For GraphSage, it has 3 kinds of aggregation methods, which are mean, max pooling, and LSTM. So mean is the most simple one. Calculate the mean value. Max pooling is choosing the max value of all of the neighborhoods feature. And LSTM is used long short-term memory to do the attention to each feature and add them together. So although the LSTM is the most complex one, but the performance show cannot outperform other kinds of aggregation method. So next we talk about the graph attention network. It will first calculate the weight for each neighbor between each neighbor and the node itself. Here we utilize the function as listed here, and we calculate the weight according to that function, and we get the E. Then we add the weight to each feature and sum them up. We'll get some kind of weighted sum. So this is kind of utilized the neighborhood's information and in a weighted sum way. The last part is the graph convolution network. It is different to previous methods because it uses some matrix calculation here. Suppose we have degree matrix, adjacency matrix, and Laplacian matrix, in which Laplacian matrix equals to degree matrix minus adjacency matrix. We find that the aggregation procedure can be concluded as this function. So if we set the function as the first one, we can utilize the neighbor's information, but we will miss the self-node information and fail to do the normalization. If we set the function as the second one, then we can use the self-node information because we add one degree matrix here, but we still fail to do the normalization. So normally we use the last function because it can consider self-node of information and do the normalization among all the neighbors. So at last, let's see the performance here. We can find that graph attention network actually outperform all of the other performance. And that's all. Thank you.